Hello and welcome to a right triangle trigonometry tutorial. My name is Kirk Weiler and today we're going to be going over some basics about right triangle trigonometry, where it comes from, how you can use it, and specifically how it's used in physics to both decompose vectors into their component parts and how to figure out the angle that a vector is at if you know its component parts. Alright, let's begin. Right triangles are really important in science, in engineering, and mathematics, right? We use them all the time in order to build things. There's a famous theorem, the Pythagorean theorem, that relates the three sides of them together. And they're extremely important, especially when they're oriented in what I would call the standard orientation, i.e. that we've got one of the legs that's, parallel to the horizon, one of the legs that's perpendicular to the horizon, and then the hypotenuse, right? And the reason that that's important is because that means there's a portion of it that is purely horizontal, there's a portion of it that's purely vertical, and there's that slanted portion, right, aka the hypotenuse. Now the way that this translates to physics is that physicists work all the time with these things called vectors, right? And a vector is something, right, as we all know, that has both length, right, and direction, has both magnitude and direction. Physicists are often very interested in taking those vectors and breaking them down into a portion that is purely horizontal, a portion that is purely vertical, and when they do that, of course, what they get is a right triangle. All right? So where is trigonometry? How does that come in, and what is trigonometry? Let's take a look at its development. All right, trigonometry really relies on the idea of similar right triangles. Now, they don't have to be right triangles, but trigonometry uses them. You can have similar figures of any type, and they're very easy to understand, right? If I took this triangle and I laid it down on top of a photocopier, and I made it larger, uniformly larger, right, then it might look something like that. If I made it uniformly smaller, it might look something like that. Now, what I mean by that is that I've expanded all the side lengths of the right triangle in the case of the bigger one so that they all get multiplied by the same number. And the smaller one, maybe they all get multiplied by a fractional number that forces the sides to get smaller. One of the things that's interesting about similar triangles in general, and of course that applies to similar right triangles, is that all the angles remain the same. Sure, the side lengths get longer or shorter, but the angles remain the same. This is actually pretty easy to see if we take that smaller right triangle and we just lay it on top of the larger one. In that case, what we see is that this angle down here must be equal, right? The two sides line up. We could shift the thing upward though, and now we see that this angle is equal. And of course, we could also shift it in that other direction to see that the right angle is the same. So it's very important. This is one of the major points of emphasis in this slide, is the idea that similar right triangles all have the same angles. If we took out our nice little protractor, right, and we slapped that thing down, right, and we put that thing on top of our triangles, what we would see is we would see all of them having that same measurement. This one, and this one. Okay? So keep that in mind. Similar right triangles all have the same angles. So what? All right. Well, let's understand similarity a little bit more. Let's say that we have this similar right triangle. Let's say it's got side lengths of 3, 4, and 5. You can use the Pythagorean theorem to see that this is, in fact, a right triangle. In other words, the Pythagorean theorem, which you've learned before in middle school, says that if I take a squared plus b squared, I'll get c squared. If, let's say, a is 4 and b is 3 and c is 5, that certainly works, right? Just to verify, 4 squared plus 3 squared equals 5 squared, 16 plus 9 equals 25, and 25 equals 25. Okay, so that is in fact a right triangle. I'm going to just clear out all this text though. Now the idea of similar right triangles, or similar triangles in general, is if I took that triangle and I suddenly, let's say, made all the sides bigger by a factor of 2. Now this isn't to scale, but let's say that I made them all bigger by a factor of 2. Obviously all the sides would become 8, 6, and 10. They'd all be multiplied by 2. Okay, again, so what? Well, the thing about similar triangles is that if I pick two sides off of, let's say, this small triangle, okay, let's say that I took the side 4 and the side 5, right? Let's say I divided them. Let's say I took that 4 and divided it by the 5. And then let's say I took corresponding sides off of this triangle, and I also divided them. Well, what would happen is I would get the same result, right? If I take 8 and I divide it by 10, I get exactly the same result as if I divide 4 by 5. If you don't trust me, take your calculator out and do 4 divided by 5 and do 8 divided by 10. In both cases, what you're going to end up seeing is that they're equal to 0.8. Now remember, these are two similar right triangles, which means all of their angles are equal to each other. Specifically, the one I'm going to be most interested in, especially if I'm a physics student, is that angle right down there. All right? And in both cases, that angle is around 37 degrees. It's not exactly 37. I think it's like 36.8, an ugliness. It's an ugly answer. But it's around 37 degrees. Now, what's really fascinating about that is it really means at the end of the day that if I've got a right triangle and it's got these sides, right, that the ratio of the two sides, it's not about this number, it's not about this number, it's really all about the angle, all right? Now, thousands and thousands of years ago, well, okay, maybe hundreds, maybe not thousands, but trigonometry has a long history. For a very, very long time, in fact, right, what people did is they realized that everything about the ratios of those side lengths boiled down to the angles and not the side lengths themselves. So it was a long development, but eventually what people came up with were what were called the trigonometric ratios. And they defined them in something that irritates people to memorize, but they said, okay, we're going to call something the sine function. Oh, that's not working. We're going to call something the sine function, but we're going to abbreviate it as sin. We're going to call something the cosine function, but we're going to abbreviate it as cos. And something called the tangent function, but we're going to abbreviate it as tan. And we're just going to define this for the angle. We're going to say the sine of an angle is simply the side length opposite of it divided by the hypotenuse. So for example, if I asked you what the sine of angle A is, you would say, well, 5 is opposite angle A, and 12 is adjacent to angle A. So the sine of A is 5/12. You might wonder, I'm sorry, not adjacent, that was terrible. I just did the tangent, that was horrible, I apologize. Divided by the hypotenuse, which is 13, so the sine of angle A is 5/13. Just what you need, more confusion, right? Likewise, I could say that the cosine of angle A is the side adjacent to it, which is 12, divided by the hypotenuse, which is 13. Now, adjacent, that word is a little bit misleading. Most people know what the hypotenuse is. Most people know what the opposite side is. But adjacent literally means to sit beside or to touch, all right? And angle A to me is touching both the side of 13 and the side length of 12. But we're always going to reserve the hypotenuse for the hypotenuse. The hypotenuse is the hypotenuse. So when I say that you have the side length adjacent to the angle, I mean the side that is touching the angle but isn't the hypotenuse. Finally, the tangent of angle A is the side length opposite of it, which is 5, divided by the side adjacent to it, which is 12. Now, we're going to be primarily concerned in physics with the angle down here, not with the angle up here. But you could certainly look at the ratios for angle B. You could say, well, the sine of angle B is the side opposite of it, which is 12, divided by the hypotenuse, which is 13. You could say that the cosine of angle B is the side adjacent to it, which is 5, divided by the hypotenuse, which is 13. And you could say that the tangent of angle B is equal to the side opposite, which is 12, divided by the side adjacent, which is 5. All right? So it's simple enough. If we needed those in decimal form, of course, we could take out our calculator and ask it, hey, what is 5/13? What is 12/13? Etc., etc. All right? We could also take out our protractors, right? Take out our protractors, and we could actually measure angle A and angle B. By the way, you might ask why I didn't set them up for angle C. We tend to not set up, at least at this ratio, or at this level, we don't tend to set up the trig ratios for the right angle. Now again, I could take this little guy, all right, let me see if I can actually draw it on top of angle A, right? So I could take this thing, I could, measure my angle by putting this at that little hole, right, and then reading up on the scale, and I could actually figure out what the angle is. Okay, but many, many years ago, people did that already for you, and they stored those ratios into your calculator as a function of the angle in the right triangle. So that's what we're going to look at next. I'm going to clear out the text on the screen, so pause it right now if you need to think about it. Okay, here it goes. All right, so how do you use your calculator? Well, I'm going to show you how to use a TI-84 Plus. So let's do that. Let's open up a TI-84 Plus right now and see how to use it. Hey, there's my calculator. All right, now angles can be measured in two primary units, if you will, the degree and the radian. We'll leave the radian for your math classes and maybe for more advanced trigonometry that you might see in AP Physics. But for right now, we want to make sure that we're all speaking the same language and that we have our calculators in degree mode. On most of the sophisticated graphing calculators, the default mode is radians, but we want it to be in degrees. So let's take this mode button right up here. Let's click on it. And let's move down to the following line. You see where it says radians highlighted, right? What we're going to do is use our right arrow key to go over and highlight degrees. All right, and now the calculator knows that if we're talking about an angle, we're talking about it in degrees and not in radians. So let's get back out to the main screen. Now remember, ultimately speaking, when I have something that looks like this, the sine of 32 degrees, what that really means is that if I took a triangle and I drew it very accurately, and I put in 32 degrees, and remember the sine of 32 is the opposite side divided by the hypotenuse. So if I drew a very, very careful drawing and I found a number here and a different number here, maybe call them number 1 and number 2, and I did it again. Apparently it's been a little bit too long since I've done right triangle trig. So here's the hypotenuse and number 2. Then when I divided those two, I'd get the sine of 32 degrees. But my calculator can tell me what that is, and it's very simple. The sine button is right here, so let's hit that. We'll type in 32 degrees. All right, let me do that myself on my own calculator here. Sine of 32, we hit enter, and then we'll round to whatever we should round to, and that's going to depend on the problem that we're working on. Right now, I'm just going to give, let's say, 4 decimal places, 0.5299. That's probably way more than what we need. Likewise, we could ask the calculator to tell us what the cosine of 48 degrees is. Looks like that is going to be 0.6691. And let's ask it what the tangent of 22 degrees is going to be. That's going to be 0.4040. Oh, I like that one. Now again, the calculator is really not doing anything magical, although it seems like it might be, but it's really just doing those ratios. So for sine, it's taking the side opposite the 32 and dividing by the hypotenuse. For the cosine, it's if we had a 48 degree angle down here, it would be taking the side adjacent to the angle and dividing it by the hypotenuse. And for tangent of 22 degrees, look at that beautiful picture, it would be taking the side opposite and dividing it by the side that's adjacent to it, and getting those messy decimals, all right? And the only reason why is they just have this table. There's just this table stored up in the calculator. It's got your angle. It's got the sine of the angle. It's got the cosine of the angle. And it's got the tangent of the angle. All right, so if you ask your calculator what is the sine of 32 degrees, literally your calculator just kind of looks over in that table, sees 0.5299, and gives it to you. Hey, that's the bell at Arlington High School. I don't need to know. I'm going to finish this up, but it might get a little bit loud in the hallways. So that's all it's doing. Likewise, when we ask it what the cosine of 48 is, it kind of goes over in our table, it looks over at it, and it figures out that it's 0.6691. Because again, it really doesn't depend on the triangle, it only depends on the angle itself, which is really rather cool. All right? So, write down anything you need to, because I'm going to clear out this text in a moment. All right, just ignore all the background talking. We'll get there. Okay, now, one thing that your calculator can also do is it can go backwards to find the angle. So let's say that we had this right triangle and we knew two sides. We knew that one side length was 7 and let's say we knew the hypotenuse was 14, and we wanted to figure out the measure of angle A, right? So I would look at that angle and I'd say, okay, which of the three trig ratios, so katoa, this is a nice mnemonic, the sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, the tangent is opposite over adjacent. Which one would involve the 7 and the 14? Well, that's opposite. That's hypotenuse. So that's the sine. So I would write down the following. I'd say, the sine of angle A is equal to 7 divided by 14. Now that happens to be 1/2, but let's not worry about it. Now remember what I was just talking about, right? Actually, let's worry about it. Let's go like this. Remember, in my calculator, we have, the angle, we have the sine, we have the cosine, we have the tangent. Now on the last sheet, what was happening is I was taking something like 32 degrees, and the calculator was going over and it was picking up the sine value. Now what's happening is I know the sine value, which is 0.5, and I need the calculator to go backwards to figure out the angle, right? That's the thing I need now. What is the angle? Well, the way that we tell the calculator to do that is by using what's known as the inverse sine. All right? So I'm going to show you how to use that right now. Let's bring that calculator back out, okay? All right, simple enough. Now we're already in degree mode, all right? And we have to literally tell the calculator to do the opposite of sine, the inverse sine. Go backwards. You're telling the calculator, hey, I know what the sine is. It's 0.5. What I don't know is what the angle is. So here's what you do. You hit the second button, and then you hit the sine button. See that? And it pops up sine with a little -1. And then you put 0.5 in, and you hit enter. And your calculator tells you 30 degrees. That's actually a nice one, isn't it? So that's interesting. This triangle has an angle of 30 degrees right there. Right there. It's really great, right? So if I actually know the side lengths of a right triangle, I can use trigonometry to go backwards and find the angles. It's really kind of cool. All right, well, pause the video now and write down anything you need to before we move on. Okay, let's do it. I'm going to clear this out. Now, what this really is about it's about physics and trying to be able to deal with the various vectors in physics through the context of right triangle trig. All right, again, one more time. As we all know, vectors in physics, right, are things that have both length/magnitude and direction. It is very often the case that we measure the direction of a vector relative to what I would call due east, right? And we measure it sort of counterclockwise, if you will. We measure that angle. So let's say that I've got this 12-pound force acting at an angle of 56 degrees with respect to due east, counterclockwise. And I want to break it down into a purely horizontal component and a purely vertical component. Well, the beautiful thing is that I've got, a right triangle. I've got a right triangle now. So what I can do is I can hone in on the angle. It's all about the angle. Always about the angle. And I can say, okay, look, if I want to find that horizontal component, and I know the angle, and I know the hypotenuse, I can say, well, let's see. I've got the adjacent. I've got the hypotenuse. Adjacent hypotenuse, which one is that? So, katoa. Oh, it's cosine, right? So the cosine of 56 degrees, hello Bell, is going to be x, which is what I'm looking for, divided by 12. I'm going to multiply by 12 on both sides, and that horizontal component is going to be the hypotenuse, or the length of the vector, times the cosine of the angle. All right, what is that? Let's get that to the nearest tenth. Let me do 12 times the cosine of 56 degrees. I'm not going to bring out our TI-84 plus right now, and that's 6.7 pounds. So that's how much of that force lies in the horizontal direction. On the other hand, if I wanted to know what y is, let me put that in green just to really kind of keep track of it. I probably should have done that in blue. But now in green, what we see is that's the opposite, and this is the hypotenuse. So now we know that sine, and the sine of 56 degrees is going to be the opposite divided by the hypotenuse. Just like before, I'm going to multiply by 12 on both sides, and y is 12 times the sine of 56 degrees. Again, easy enough to do on my calculator. 12 times the sine of 56 gives me 9.9 pounds, almost 10 pounds. So that's kind of cool. That means that we've now taken this vector, right, with a magnitude of 12 at an angle of 56 degrees, and we've broken it into a horizontal component of 6.7 pounds and a vertical component of 9.9 pounds. And that can, of course, have all sorts of different effects within physics in terms of the way that you analyze forces, and even, it doesn't even have to be a force, right? It could be any vector in general. Now, just as a side note, right, and it's not a minor side note at that, it's actually quite major. If I have a vector, and I know its angle with respect to due east, so I know that angle, let me call it angle A, then the horizontal component, all right, will always be dictated by the cosine of A, and the vertical component will always be dictated by the sine of angle A. And you just multiply those by the force's magnitude. I don't want to just say the magnitude, I don't want to just say the force, because the force is a vector. So you multiply that by the magnitude of the force, or the force magnitude, and you get your horizontal and vertical components. So cosine is the natural way of thinking about the horizontal component. Sine is the natural way of thinking about the vertical component. That is assuming that you're measuring the angle from due east counterclockwise. All right. Well, pause the video right now, write down anything you have, and then we'll go on and do one last thing. All right, I'm going to clear it out. Let's do one last piece. What if we know the components and we want the angle? All right, so sometimes you've got the vector, you've got the angle, and you want to break it down into components. That's what we did last time. Sometimes you actually know the components and you want the angle. You probably also want the magnitude of the force, but we're not going to be too worried about that right now because that's just the Pythagorean theorem. So let's say that we had some vector, and we knew that it had a 3-pound horizontal component, and it had a 7-pound vertical component, and let's say that we were looking for that direction angle from due east. Well, what I'm going to do is I'm actually going to use this right triangle. Ooh, still in green. I'm going to use that right triangle, and I'm going to find this angle. I'll call it A. All right. Now, what do I know? Well, I know the side opposite of it, and I know the side adjacent to it. So then I think about my 3 trig ratios, SOHCAHTOA, and I say, the one that involves opposite and adjacent is tangent. So I can actually say the tangent of angle A is equal to the side opposite of it, 7, divided by the side adjacent to it, 3. Now remember, what I don't want to do right now is take my calculator out and plug in tangent of 7/3. That's not going to do me any good. In fact, what I need to do is use that inverse tangent again. So I hit second tangent on my calculator, and then I enter the fraction 7/3. Again, I'm not really sure what we should round to here, but for me, that comes out to be 66.8 degrees, which seems about right given the picture. That's it. So pause the video now and write down anything you need to. All right, let's clear out that text and let's finish up. Trigonometry is one of the absolute most important topics in all of mathematics, primarily because of how often it gets used in physics. A firm understanding, or at least a firm exposure to right triangle trigonometry, is absolutely essential to be successful in physics, primarily because we want to use it to be able to decompose or break vectors into their component parts. All right. As well, we'd like to be able to take vectors that are written in their component parts and figure out what direction they're headed in, and by definition, that means figuring out an angle. The last few problems in this particular video were along those lines. So, I just want to thank you for joining me for a little bit of our right triangle, physics, and math sort of tutorial to get you up to speed. I do hope it helps, and until next time, keep thinking and keep solving problems.